I hope this is clearly visible to you. So we have to do alkanes, in which homologous series, physical properties, melting, boiling points, and density, and effect of branching on them. Preparation from alkyl halides and aliphatic carboxylic acids, reactions, combustion, halogenation, including allylic and benzylic, halogenation, and
ఏ 18 మంది రా.
అవురా?
I think I forgot not to allow you people to unmute yourself. I did it now. I hope I'll not be disturbed anymore like that. If you have any doubts, you can raise your hand. I'll discuss them. So as I said, then we have to go for alkenes and alkynes. Sorry, we preparation from alkyl halide, aliphatic carboxylic acid reaction, combustion, halogenation, allylic, benzylic, halogenation, and oxidation. So primary focus is alkanes today. Okay, if time will permit, then we'll go to alkenes, dienes, and alkynes. Otherwise, our primary focus is alkanes. Okay, then alkenes and then benzene. So let's start. Now, before I start alkane as such in specific, I want to discuss this word saturated compound and unsaturated compound, which I found several students remain confused even at very later stages. Now see, saturated compounds, compounds which have only carbon-carbon single bond, no carbon-carbon multiple bond. When we talk of the word saturated compound or unsaturated compound, we are talking of a chemical condition, not of any mathematical expression. Degree of unsaturation is not we are discussing. We are discussing saturated compound. Acetone is called a saturated compound. Okay, saturated word is only related to the carbon-carbon multiple bond, not with any other. Okay, compounds which have only carbon-carbon single bonds, no carbon-carbon multiple bonds, these will be called saturated compounds. Unsaturated compounds are the compounds containing double and triple bonds between carbon atoms besides single bonds. Okay, such compounds which contain double bond and triple bond between carbon atoms besides single bond. So there may be several single, but even if one site has a double or a triple bond, you will call it an unsaturated compound. Again, I am emphatically saying it is a chemical condition. An unsaturated hydrocarbon must, please note the word must, give electrophilic addition reactions of bromine, that is decolorization of bromine water. That is a compulsory condition we want for a compound to be referred as unsaturated compound. Okay, for that we need this condition. Now, when I talk of degree of unsaturation, then it is entirely different. When I talk of the word degree of unsaturation, the number of hydrogen molecules required to convert 1 mole of given molecule, any of these molecules from left hand side, you can see, to convert 1 mole of given molecule into fully saturated. Fully saturated here, I mean each and every possible bond in the product has to be single bond. Fully saturated. Now I don't want only carbon, as well as other atoms should have single bond between them. This is a compulsory condition we want, that fully saturated open chain structures. So not only fully saturated, we also want them to have a open chain. If it is cyclic, it need to be open. Then that mathematical value of number of hydrogen moles required for one particular mole of molecule of a substrate to convert, as I just said, is called degree of unsaturation of this particular compound. For example, if I see here, this double bond is converted to single bond. So I'll write 1 hydrogen because 2 atoms, 1 hydrogen, done. So degree of unsaturation is 1. Here, when I say overall, it was a saturated compound, but it still will have 1 degree of unsaturation because C double bond O will be converted to C single bond O. Cyclohexane, there is not even a single pi bond here. It is a saturated compound as such, but it will have a degree of unsaturation because that open chain thing is to be achieved. Coming here, 3 pi bond, 1 cycle. So I'll need 4 hydrogen mole of molecules to convert it to N-hexane, and therefore this is the degree of unsaturation of benzene. Okay, there are some other names also with which degree of unsaturation is referred, and they are, if other names to be referred, DOU is also called index of hydrogen. Okay, it is called index of hydrogen deficiency. Then it is called double bond equivalent unsaturation index. These are all other names for the particular property. Degree of unsaturation in questions may be referred as index of hydrogen deficiency, double bond equivalent. Okay, double bond equivalent, so they will write it DBE. This is for this. Okay, index of hydrogen deficiency, IHD, sometimes you may come across. If you come across these words, they are basically just talking of degree of unsaturation. And yes, there is some formula also, but in phase 2, I don't think you need that formula. You need the basic concept. If you are done with the concept, you can go for the formula. Practically, I will not promote that formula much because it is just the basic concept which will do the purpose. Next is alkanes. Now let us go into alkanes. Now alkanes, as I said, are saturated compounds, CnH2n plus 2. They are also called paraffins. Okay, preparation of alkanes by hydrogenation of alkenes and alkynes. That is the first, and I will say the most important method for exam. Okay, so many crucial questions are from this. So by hydrogenation of alkenes and alkynes, if I want to hydrogenate, I'll need 2 moles of hydrogen. Alkenes, then I'll need 1 mole of hydrogen to form a saturated alkane. Yes, the catalyst word that I referred here could be any of these. I can use nickel hydrogen, platinum hydrogen, palladium hydrogen, rann-nickel hydrogen. Okay, Wilkinson catalyst. Wilkinson catalyst का नाम, what is the name of this Wilkinson catalyst? It is tris triphenyl phosphine rhodium 1 chloride. Okay, it is tris triphenyl phosphine rhodium 1 chloride, that is called Wilkinson catalyst. Rann-nickel hydrogen can be used. Nickel hydrogen, platinum hydrogen, palladium hydrogen, all these can be used for this saturation or hydrogenation purpose. Absolutely okay. Now see, rann-nickel is a nickel aluminum alloy. It is much more efficient and could be a better choice than any of first 3. In fact, these 2 both are good choices. Now see, important point to remember for exams I am talking, okay? For hydrogenation reaction. First of all, hydrogenation by any of the above catalyst is a syn addition reaction. Syn, it is like from same side the hydrogen is approaching. Now to exemplify, I am using the isotope deuterium D2 in presence of nickel catalyst. Correct? Now, how they are doing? See, I am taking cis-2-butene. This is sp2 hybridized planar molecule, right? This is sp2 hybridized planar molecule, and when deuterium is added, this and this both carbons, then either the deuterium will come. See, it is a planar molecule. So these are all sp2 like this, trigonal planar. If deuterium is coming from top side, this will go down side, and they will become, one is this bond and three are these tetrahedral. Okay. Other thing is deuterium can come from downside and this two planar things will go upside. So two equal probabilities are there that it can come from upside or it can come from downside. Deuterium from upside or deuterium from downside. See, and here you can see once I form this, it is a mesomer. Whether downside or upside, it doesn't matter anymore because these two CH3s are ultimately generating a meso. Deuterium ka image deuterium, CH3, CH3. Okay. But please keep a full attentive eye on the question. Here I had two groups identical. So I had the meso. If the groups are not identical, see here I have taken one CH3 and one is ethyl. Then you have to be aware and attentive that in such a condition, okay, in such a condition, when it is methyl and ethyl, then it is no more a meso because methyl and ethyl are not forming image of each other. So now I have to write both the cases as separate cases, that deuterium coming from upside this particular structure, downside this particular structure. If you can visualize just that, if I keep this structure above, let me say this structure is A, and then I imagine a mirror here and put this structure as B as such, just over here, that here is B. You can see how they are exact mirror images of each other and certainly non-superimposable. So non-superimposable mirror image of a molecules are formed and thus it is acting as a racemic mixture. So as a result of syn addition, I am getting a racemic mixture. So whenever you do this, that cis alkene, syn addition, meso or erythro pair. So this E is erythro pair, cis, syn, meso product or erythro pair. Erythro pair, when I say, then it is always a racemic mixture. Okay, so just don't go blindly and put an answer on meso. Please take a note that what type of alkene is given in the question. If the same thing I do with trans, then the shorthand for that is transalkene anti-addition. We are at syn addition. So T-cert, transalkene syn addition, racemic trio pair. Here it is a trio pair. Okay. Again, doing the same thing. If they are identical, up and down, how will I get? Up I go or down I go, I'll get this. So ultimately they are mirror images. They are trio compounds. Okay. Now as it is already a mirror image, so I wouldn't say what would be the difference if I take ethyl, methyl or anything. It will remain a trio pair. Important. If you have a conjugated diene, okay, if I have a conjugated diene and that too, if it can be rotated to cissoid conformation, okay, if it can be rotated to cissoid conformation, then you will observe 1,4 addition to be the major product and 1,2 to be the minor. See how 1,4 I am adding. Coming here hydrogen and here hydrogen and bond is shifting to center. So 1,4 addition is major product and 1,2 addition is minor product only when it can rotate to cissoid. For example, if I have out of these like this, then this is already cissoid, but this is not only transoid, it cannot rotate to cissoid. Okay. So this cannot rotate to cissoid. This will give only 1,2 addition irrespective of whatever I do. This will give me 1,4 addition. Is that absolutely clear how it is done? With increase in steric on multiple bonds, ease of hydrogenation will decrease because the entire process is based on adsorption on metal surface. And if there is something which is increasing the steric, then definitely the adsorption of that particular molecule will decrease, and thereby the reaction will decrease. Okay, so decreasing order of magnitude of heat of hydrogenation or stability is inversely proportional to heat of hydrogenation is a very common thing जो आपके दिमाग में होगी. Okay, you might be familiar with this, that stability is inversely proportional to delta H hydrogenation. This you can use only and only when the products formed are identical. You cannot use it anytime, anywhere. Only when products are identical, then you can use that stability is inversely proportional to delta H hydrogenation. Is that absolutely clear? Now, if stability is inversely proportional to delta H hydrogenation, only when products are identical. This you keep in mind. So come here. Now, if I talk of decreasing order of magnitude of heat of hydrogenation, certainly we have utilized it as and when the products are same or not. Easiest hydrogenation and highest value of heat of hydrogenation was found to be of acetylene amongst alkene we are talking, and benzene. Then comes 1 hour, then 2 hours substituted. Okay, increasing the steric will decrease the rate and thereby the heat of hydrogenation. Then comes alkene. Okay, after that, 1 alkyl I introduced. See, more the alkyls introduced, more will be the hyperconjugation. More the hyperconjugation, more will be the stability of alkene, less will be the ease of hydrogenation, and thereby less will be the heat of hydrogenation too. Okay, now come here. If I talk here, see cis, when I talk heat of hydrogenation, order is this. Cis is having more. After cis, it is same carbon having 2 alkyls. Okay, this is having 27 kilocalorie per mole. And this is having 27.6 kilocalorie per mole. Okay, these two are practically concluded by in the order of stability. Okay, these are heat of combustions I have added extra. So these we go by their heat of combustion to conclude that what is more stable when we conclude that which alkene is more stable. Okay, then comes the 3 alkyl, then comes the 4 alkyl, and benzene is like least of all. Just to add in the order, I'll add, otherwise it's of no importance. Metal hydrogen do not reduce acid and derivative except RCOCl. Please take this as a very important note. It was a question asked in 2016 advance. Okay, 2016 advance clearly mentioned that there was a question in which they did not reduce acid and derivative with nickel hydrogen. So that is why I'm saying metal hydrogen. So please go through NCERT for any more confusion or clarity. If you have, because it is given in NCERT, from there only I am taking that it will not reduce the, it will not reduce acid and derivatives. Okay, but if you have any other type of reagent than metal hydrogen, then don't generalize that how it will behave. It entirely depends on individual compound. Okay, so then we cannot say how the things will be. Coming back to where we were, metal hydrogen reductions we just did. So RCOCl will be reduced to alcohol. Now see, this was a simple question which appeared in 2020, and you can expect similar in different exams. Which of the following compounds produces an optically inactive compound on hydrogenation? Now, no selective hydrogenation or nothing is asked. It was simple that if you have a multiple bond, this multiple bond is reduced to alkane. Okay, direct question was supposed to be asked. Simple. You just form the product. Approach is very direct. Form the product and check whether the compound is chiral. And in this process, always take care whether that compound is chiral by the existing chiral center, or in case a new chiral center is generated or something about that is asked. So that is why I always ask you to form a complete product and then comment. Don't comment before that. Okay. See here, you formed and you see, okay, this particular compound is still chiral. HCH3, this group is different, this is different. If I form this, this is a chiral. Okay. If I form this, this is chiral. Let us check this HCH3 and this side. So this is still chiral. Okay. So answer is 2. Answer is 2. So the precaution you need to take care is form the product and then only comment. Otherwise, do not comment blindly or guessing in the air. Okay. Don't do that. From alkyl halides, when we want to check from alkyl halides or prepare alkanes from alkyl halide, I have 2 methods. One in which the carbon count will change and one in which the carbon count will remain same. So first I am talking in which there is a coupling reaction and thus there will be the change in carbon count. So Wood's reaction, R1X plus R2X, sodium in dry ether, R1, R1, R2, R2, R1, R2 and NX is formed. And if R1, R2 are identical, then better yield of alkane and it is called simple Woods. If MeCl, MeCl, then you will get ethane. And as MeCl is the smallest possible alkane I can have, so the smallest Woods product I can produce is ethane, not the methane. I cannot produce methane by this method. If R1, R2 are different, then it is called mixed Woods and definitely poor yield because the number of products obtained will be more and the yield of my individually desired product will be less. If 2 halogens are present within the molecule, then it is called intramolecular Woods. Molecule के अंदर ही अंदर अगर halogen combine कर रहे, then it is called intramolecular Woods. Okay, and this intramolecular Woods reaction will result in cyclic compound formation. Correct? Or sometimes unsaturated compounds also. See, we were preparing saturated alkanes, but this intramolecular Woods can form the unsaturated compound, vicinal dihalide, right? Woods reaction. So the 2 radicals formed adjacent immediately will form a bond. If it is 1,3, then cycloalkane. So cyclopropane. 1,4 position, this 1,5 I can have cyclopentane. 1,6 position dihalo I can have a cyclohexane. Other than Woods condition, that is sodium in dry ether, I can write zinc or magnesium or lithium. Any of this will give me the same product in this particular reaction. And as I already told you, methane cannot be prepared. Now, methane, you can say this could be the method, but this is not possible. Why? Because if I say HX, it is hydrohalic acid and sodium in halic acid, then these two will react and I'll have a liberation of hydrogen gas, not any coupling reaction. Correct? Now coming to this JEE 2005 old question, this type of positioning is there. And the options were that if 2 molecules combine and dimers are formed, see 1, 2 and 3, 3 options were based on intermolecular, 2 molecules colliding and forming a product, intermolecular. And 4th option was based on intramolecular Woods. So wherever there is a possibility of any intramolecular reaction versus the intermolecular reaction, intramolecular reaction will dominate. Okay, intramolecular reaction will dominate because of the reasons of entropy. Because the bond formed is same carbon-carbon. Bond formed is same carbon-carbon in inter or in intra. But as when the 2 molecules will combine, then the entropy of the system will decrease. Whereas here it will remains same, and thereby the fourth will be preferred because the entropy is not decreased in this reaction. Clear? This is one of the important question. Never ever go by inter if there is a choice of intra. And intra is possible from cyclopropane to cyclohexane formation. So here it is a cyclopropane. In irreversible reaction, don't think that this is a strained structure or an unstable, because for an irreversible reaction, you are always bothered about the kinetics of the reaction. Whatever is possible faster, whatever is possible favorably with less activation barrier is the path chosen by the reaction in irreversible reactions. For thermodynamics stability of the product to be considered, a reaction has to be irreversible. If it is irreversible, reaction has to be reversible. If the reaction is reversible, then you can talk of which product is thermodynamically more stable should be the major product formed. Is that clear? Next comes by reduction of alkyl halide. Now this method will be the one in which the carbon count remains same. I did not discuss the exact mechanism of Woods. I don't think that is what is actually needed. I am going for the major question concerning portions. If there is anything related to mechanism also for question, like I am concentrating on phase 2. Okay, not like phase 1 that there are two mechanism of Woods, which one to use, when to use. That is not what is required for phase 2. So by reduction of alkyl halide, second method is by reduction of alkyl halide. When I talk of reduction of alkyl halide, carbon count between alkyl halide and alkane will remain same. Now, if I say the carbon count will remain same, then how will I do the reduction? Very, very important. Zinc, dilute HCl or acetic acid. Zinc is dissolved in dilute HCl or acetic acid, except fluoride. Here, the alkyl halide to be used should be anything but RF. Except RF, I can use any of these and we'll get RH, ZnCl2 or zinc acetate. Now, how this is possible? Because the zinc is metal, sufficiently reactive, in fact, amphoteric, and it reacts with dilute HCl, liberating nascent hydrogen. It is a reducing reagent. I can say that somewhat like zinc. In case of zinc, we had RR coupling. Na? Same way, zinc in HCl, somewhere organometallic could have been formed and RH is formed. See, zinc, if it was vicinal, then you form this alkene. But if it is zinc in HCl, then form this alkene. So take care. If it is alone zinc, then it is not reduction. It is like coupling reaction. Okay, so gadda is like a possibility of error. Please take care which way the thing is written on the arrow. With zinc, you can follow somewhat like Woods. With zinc in HCl, follow the reduction. Absolutely okay. Take. Moving further, from carboxylic acids. There are two ways from carboxylic acid. Again, one is a decarboxylation method by directly soda lime, and one is somewhat coupling type. Carbon count will increase. Though I cannot say this time that this method having the same carbon count, here also there will be change. But how and when, let us see. So from carboxylic acid, I have first method is Oakwood degradation. Name hai iska, if you can remember, very good. Or not, just soda lime decarboxylation is something which you can keep in your mind. Soda lime decarboxylation is known as Oakwood degradation. Now, what happens in this decarboxylation? Sodium or potassium salt of carboxylic acids on heating with soda lime, which is mixture of NaOH and CO, form alkanes with one carbon less than the original carboxylic acid. That is called soda lime decarboxylation. You will just remove this red CO2 part and will do no other change. Okay. Sodium or potassium salts of carboxylic acid on heating with soda lime, mixture of NaOH plus CO, form alkanes with one carbon less than the carboxylic acid. This method is primarily a carbanionic method. Now, here I need to tell the mechanism. This RCONA. Okay, this RCONA, it could be sodium or potassium. I am exemplifying with sodium. When I heat it, it is fundamentally RCO minus Na plus. This loses CO2. CO2 is gone and I will have R minus Na plus. So carbanion is formed and this is my RDS. Okay, so I can say that rate of soda lime decarboxylation is directly proportional to stability of carbanion involved. Okay, it is directly proportional to stability of the carbanion involved. Then it is called, this will be used to decide the rate. Like for example, if I'm asked that we have CH3CONA, CCl3CONA, okay, and say CH3CH2CONA, what will be the order of their soda lime decarboxylation? Then you will simply say that this is, if I call this as a 2, rate of soda lime decarboxylation of 2 is better than 1, is better than 3, because CCl3 minus best stable out of these 3, then the methyl, then the ethyl carbanions. Is that clear? How to decide? You have to decide on the basis of the carbanion involved. Absolutely okay. Now in questions, they may not give the sodium or potassium salt. It could be a possibility that they will give you the carboxylic acid. Okay, for example, if I am given CH3COH and on the arrow I am given NaOH plus CO, doesn't matter. Please answer absolutely same way, right? CH3 and H, CO2 gone. Why? Because anyhow this will form the acid-base salt. Na? Either they give directly or don't give, doesn't matter. It is a non-aqueous condition, direct heating in which we are achieving. Still there will be acid-base reactions. And you will get this reaction RH plus Na2CO3. Na2CO3 is the byproduct. Now the purpose of CO in this, why we are using CaO in this, so decrease the melting point of NaOH, which is relatively high. So that is one purpose, and absorbing of CO2. NaOH can absorb, but as compared to NaOH, CO is a better or faster absorber of CO2. That is why we are using CaO just to support the reaction. Even in absence of CO, reaction could have been possible, but then I might have to heat for a higher temperature or a longer duration, which we don't know how much. Okay. Next is sodium salt of which acid will be needed for preparation of following compounds. Okay. Now this question was like sodium salt of which acid will be needed for the preparation of following compound. Consider this with a soda lime method. Okay. So if I have to prepare ethane, I will need propionic acid salt, as I'll remove this CO2. If I want to do the same reaction with ethene, so that is, propane, for propane. So I have to take an acid with one propane is ready and one extra CONA you will put like this, and this is your answer. When it is ethene, then I have to take this. But practically it will be very difficult because here is a resonance stability and this double bond will be generated here. Right? Will be existent due to resonance, and therefore this is a very difficult reaction. Cyclopentane, no problem. In case of cyclopentane, you simply add cyclopentane per extra CONA. Is that absolutely okay? If you have any doubt, you can raise your hand. Or the best thing is you can keep writing in your notes, and in the end, you can raise your hand and ask. After the lecture, I'll wait individually for your doubts, and others can then move out of the class and I'll solve doubts. Okay, no problem with this. Coming to the next method from acids. Next method is very, very important. Already I'm taking only important portions, so there is no point in saying repeatedly very, very important. So coal-based electrolysis. Now, if we talk of coal-based electrolysis, see, R1 and R2 are, I'm taking the two acids which are like different. That is why I'm pointing out R1 and R2. So R1CONA or R2CONA. Okay, two acids I am taking. And when we do electrolysis, electricity se bond fission, now what are the combination? R1 can combine with R1, R1 can combine with R2, or R2 can combine with R2. These are my three possibilities: R1, 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 R2, or R2, R2 combinations. And the other byproducts will be Na2CO3 and hydrogen. That I'll explain. For this, I'll use the mechanism also. R1, R2, if I take ethyl for explanation, then this is my acid. This is what I will get. CH3CH2CO minus. Right? Just as the conditions are aqueous, I'm just ionizing. Now on anode, anion will go. And on anode, one more thing is fixed, that anion will go and oxidation will take place. So as you can see, this anion I have brought here. Oxidation means loss of electrons, forming this negative. So I will have a C2H5CO dot. A radical is formed. Now this radical is losing CO2. Okay, this is losing CO2. So as 2 moles of this carboxylate I have considered, to 2 moles of CO2 gone, and I am getting 2 ethyl radicals, CH3CH2 dot. Now 2 CH3CH2 dot when interact or when combined, then N-butane is formed. Is that absolutely clear? We are forming N-butane. See, if my acid had 3 carbons, I am getting 4 carbons in the product. Okay, so I can say if we start with the carboxylic acid having n number of carbon atoms, then the alkane formed will have 2n minus 2 number of carbon atoms. Okay, if the acid has n number of carbon atoms, then the product will have 2n minus 2 number of carbon atoms. Perfectly fine. On cathode, reduction will take place. And on cathode, what will I bring? I'll bring cation. Right? So this cation Na plus under aqueous conditions. But as you know, the reduction potential of hydrogen is higher. H plus, I should say, not hydrogen. H plus to H2 is higher than Na plus to Na. So hydrogen is reduced. So at cathode, always hydrogen will be reduced. But at anode, alkane is formed. Alkane is formed at anode. Yes, at anode also hydrogen could be released if the acid used is formic acid. When this ethyl is replaced by H, that is formate, formic acid salts, then you will have hydrogen at anode. Cathode, irrespective of what acid is taken as a starting material, always hydrogen is released. But in anode, only when formic acid salt is used. Again, as you have seen that it is a combination reaction. 2 are combining. 2 alkyls are combining. So methane cannot be prepared again by this method. Okay. As I have said, anode, sodium formate will give hydrogen. With completion of reaction, pH of solution will increase. Okay, here I want to say, with completion of reaction, pH of solution will increase. Why am I saying so? Let me tell you. See, initially the aqueous condition was having sodium salt of carboxylic acid. and afterwards it is having a sodium salt of Na2CO3. Okay. Now carboxylic acid are stronger acid than H2CO3. That is why they displace H2CO3 from salt and liberate CO2. So stronger acid, salt. Whereas here it is relatively the salt is further getting weaker and base is remaining same, sodium, NaOH, right? And the acid component is getting weaker. The pH of the resultant electrolyte will be more alkaline. So it will be increased with completion of reaction. pH of solution will increase. Correct? Which of the following reactions produce propane? Now, this was a JEE Advanced 2019 question. So be careful. Again, propane is asked. And see, zinc. I have already told you, first thing is check the reagent zinc plus dilute HCl is reduction. So yes, you will have the same carbon propane formed. Zinc, then it is dehalogenation and I will have propene as answer. Right? So A was the answer, B was not the answer. Soda lime. If I remove this CO2, 1, 2, 3, propane is possible. C could be the answer. Electrolysis, if I do, then 1, 2, 3, if it combines, then I'll have 6 carbon and hexane will be formed. So answer is A and C. Is that absolutely clear? Now, this was such a basic question. They are not asking something which is very confusing. Just need your proper attention towards the paper 2019 direct question from hydrocarbon chapter from alkane. Okay. Oh, physical properties of alkanes. Usually people consider physical properties like very easy and can go. No, please do the physical properties carefully. These days, questions from these tables and the compound properties are coming. So be attentive. First, physical properties of alkanes. C1 to C4 are gases at room temperature. If I talk from C1 to C4, they are gases. Please, alkanes only I'm talking. C5 to C17 are liquid at room temperature. So methane to butane are gas, pentane to C17 tak it is liquid, and C18 onwards are solid. And when I talk of solid, it is like soft solid, like Vaseline, not hard solids. They are relatively softer solid as there is no stronger intermolecular force of attraction except for the simple van der Waals force of attraction. Density of all alkanes is less than water and therefore they float on water. Density of all alkanes, whether it is light or like smaller molecular mass or bigger molecular mass, they all float on water. With increase in molecular weight, boiling point of alkanes increases. Okay, for isomeric alkanes, this is important. For isomeric alkanes, with increase in branching, boiling point decreases. But otherwise, you are not bothered about branching. First, you will check the molecular weight. More the molecular weight, higher will be the boiling point. Okay, now this is from NCERT data. Let us just verify. See, methane, ethane, propane. This is your one question. Or rather, I'll take also this butane. So if you check this, there is a continuous increase in their boiling point. Right? So with increase in molecular weight. Next question. Methane and 2-methyl propane. Butane and 2-methyl propane. See, they are isomeric, same molecular mass. Now, next one is more branched. See how the less branch is having higher boiling point. Clear? Again, let us see isomeric. We have pentane, 2-methyl butane, 2,2-dimethyl propane. Down I am moving, branching is increased. So you can see how the boiling point with branching is decreasing 309 to 300 to 282. I hope you are absolutely okay with this thing. Whereas again, there is a continuous rise of molecular weight, right? See 86, 100, 114, 128, 140 to 282. So again, you have a regular increase in boiling point. Okay, 341, 371, 398, 423, 447. This is from NCERT. So what you concluded, only when they are isomeric, then only you talk of branching. Okay, more branch will have less boiling point. Compare a more branched pentane, which is this one, versus butane. See, now you cannot say the branching more, boiling point less. This is applicable only when they are isomeric. Is that absolutely clear? And this we have directly taken from NCERT. Now, if I go to have a similar order in boiling point, I don't think I'll be able to talk much. Okay, you can see if let me draw and please help me if I go somewhere wrong. Methane 90.5. So this is, let me change the color. If I say this is methane, CH4, it was 90.5. Then next is ethane, 101. Let me put a little like this, 101. This was C2. Then C3 is 85. It is dipping as compared to my methane. Slight dip here. Slight dip here. Dip is not very high, but yes, there is a dip. 85 degree Kelvin, and this is C3. If I talk of C4, 134, so definitely going up. 134, this was C4. C5, 114. So it is coming down, but still above this. So I'll say somewhere here, C5, 140. Right? Then C4, it was just the branched one, 114. So I'll not take this. I'll go to C5 pentane, which is 143. If it is 143, I'll go up here. It is C5, 143. Correct? Then let us go to C6 hexane, 178. So it is going up. 178 C6. Right? And C continuous 182, 216, 222. So continuously increasing now. So all I can say is C1, C2, C3, there is some issue. After that, it is increasing. Continuously with increase in molecular weight. Unbranched cases, we have a direct increase in their melting point. Only in initial C1, C3, you found this something that C2 is higher than both C1 and C3. And then there is all rise. Now let us compare, is there any effect of branching on these melting points? So see, more branch is having less melting point in case of butane. Let us see in pentane. If I go pentane, this is not true because you can see more branched is having lesser melting point. Anna, but again, there is no regular order, right? If I talk of pentane to 2-methylbutane, more branches having less. But if I talk to 2,2-dimethylpropane, it is in fact the highest. So there is no regular relation which you can predict in general for melting point with respect to branching. Unbranched cases, you can predict that with increase in mass, the melting point will increase except for C1, C2, C3, which has a mountain appearance. Okay, in fact, C3 is the lowest. I hope you have absorbed this point. Moving further. Oh, yes, this question of mains 2020 is like very different question, I would say, or rather, I would say it was a more data based. A flask contains mixture of isohexane. When they are talking of isohexane, let me draw the structure for you. What is isohexane? 1, 2, 3, 4, 5. This is my isohexane. And 3-methyl pentane. 1, 2, 3, 4, 5. This is 3-methyl pentane. One of the liquids boil at 63 degrees centigrade while the other boil at 60. Now you don't know which one boils at 63 and which one will boil at 60, as both are having only one branch. Okay, so either you know it or you don't know it, but still if you go by random logic, this is more symmetrically branched or something. So this should have a like God knows higher boiling point or not. That is a very vague thing I'm saying. Better to go by data. One of the liquids boil at 63 while the other at 60. What is the best way to separate and which one will be distilled out fast? So when this question came, there were options, of course, fractional distillation, simple distillation, and all those things. But the problem was that it was a data-based question. Now, 3-methyl pentane has 63 degrees centigrade and 2-methyl pentane has 60 degree centigrade. And that was the problem. Okay, because only one branching, just position change. Either you know it or you don't know it. And as the difference in their boiling point is so close, so less, so best method for separation, if I go for distillation, then it is fractional distillation. And which one will distill out first? The one which will have lesser boiling point will evaporate and will distill out first. So it is lower boiling point is of isohexane. So isohexane will distill out first. Okay. Additional information, I have just added this for your information. Like if someone makes the question on the same ground, then 2,2-dimethyl butane has 50 degree and 2,3-dimethyl butane has 58 degree boiling point. So you can have a question on a similar concept, but this compound. So just take a screenshot of this data. Okay. If this question is repeated with this, then which one will distill first? 2,2-dimethyl butane will distill first. These are just other isomers of hexane only. Okay, moving to next. Coming to, these were the preparations from the, I think all the things which were asked, we have prepared from that. Let me once go through. Where were we? I think here we were, 22 page number, chemical properties, yes. And we have, so homologous series, physical properties, melting boiling point and density. Density, we have already said that all of them will have less than 1. And effect of branching on them. Preparation from alkyl halides, done. Aliphatic carboxylic acid, done. And moving to reactions. Okay. So we are coming to this last set of this chapter, this alkanes chapter. Let us go to this last set. And one, let me go here also. This we have done. Chemical properties. So if I talk of chemical properties, as they are called paraffins, and paraffins meaning they are lazy. It means lazy. Lazy means they are less reactive. If they are less reactive, then there will be less number of chemical properties to learn and to do the questions. So fine with it. We are happy with it. No problem. First and foremost is combustion. Combustion is certainly highly exothermic. That is why they are used as fuel. Okay. So CnH2n plus 2, it boils with 3n. This is just a balancing oxygen. Okay. We are boiling it with oxygen, forming NCO2 plus N plus 1 H2O. Is that absolutely clear? So delta H is highly negative exothermic reaction. If oxygen or air is insufficient, then carbon black is formed, which is used in printer ink, carbon filters, etc. Carbon filters are used in those AquaGuard, the water purifier things. Okay, these carbon filters are used in water purifiers. So if we go by this reaction, you can balance this reaction. I don't find any difficulty कि आपको होगी इसमें. Just remember it is highly exothermic. Yes, that was an uncontrolled oxidation. When I was talking of combustion, it was an uncontrolled oxidation in ample supply of oxygen. But if I do controlled oxidation, then there is a limited oxygen supply plus some catalyst or condition, and we stop by at particular point. Now, this is something which is written in NCERT and is usually to be remembered. Okay, so I have taken this cutting from NCERT. Please remember this. See, methane with copper at 523 Kelvin, 100 atmosphere is forming methanol. Alcohol is formed. So with copper, methanol, alcohol. With MO2O3, same methane, aldehyde, al is formed. That is methanol acetaldehyde is formed. Okay. When you go to ethane and 3O2, then manganese acetate. Now see, acid derivative, ek tarah se acetate, salt of acetic acid, and then you are having oic acid. Then this ethane is forming ethanoic acid. So from alcohol to aldehyde to acid, 3 methods with different catalysts. Please repeat, take notice in your brain that with copper, methanol, with MO2O3, methanol, and with O2, they are forming ethanoic acid. Absolutely okay. Ordinarily, alkanes resist oxidation, but alkanes having tertiary hydrogen atom can be oxidized to corresponding alcohols by potassium permanganate. See, Me3CCH, KMnO4 oxidation. Then you are having 2-methyl propane 2-ul is formed. Is that absolutely clear? And only this tertiary H will be oxidized, nothing else. It is very specific, only for tertiary H atom. No other thing is touched. Otherwise, no such oxidation with KMnO4 will be observed. It is a common thing for alcohols and aldehyde ketones to get oxidized further. But here specifically, ordinarily alkanes resist oxidation, but alkanes having tertiary H atoms can be oxidized to corresponding alcohol by this method. Next reaction is third number, isomerization of alkanes. So see 1, 2, 3, 4, 5, 6. This thing I am explaining with 6 carbon alkane. Remember the catalyst of isomerization and aromatization. Isomerization is anhydrous AlCl3 plus HCl. Aromatization is Cr2O3 or V2O5 or MO2O3 supported over alumina Al2O3. So if I talk of anhydrous AlCl3, HCl, it is isomerization. Carbon count will remain same. Carbon-hydrogen linkages count will remain same. Only there is some change in structural isomerism. So it was a linear isomer and now it is getting branched. Now when it is getting branched, always remember that this thing will be possible only when less branched alkane will become more branched alkane. Reverse in some Indian author books like Arihant, etc. They have written at this temperature you go forward, at this temperature you come backward, which is not correct technically, because the sole driving force for this reaction, see delta G is equal to delta H minus T delta S. This reaction spontaneously goes only forward only. Delta H is 0. Now only factor to support this reaction is increase in entropy. Okay, increase in entropy matlab lesser intermolecular forces of interaction, and lesser intermolecular forces of interaction can be achieved when more branching is there. More branching, less intermolecular van der Waals forces of attraction. More branching, then less intermolecular force of attraction. No branching, or less branching will have more intermolecular force of attraction, van der Waals force of attraction, molecules are more attracted to each other, entropy will be less. Okay, so I want this delta S to be positive or 0 to keep this minus T thing negative, thereby delta G negative. Okay, so ideally this reaction always goes from less branch to more branch. Reverse is very difficult, or some way they do, I don't know how can they do. Otherwise, if I increase temperature, doesn't make the change in the entropy thing, right? What I want to say, that then it will become a delta G positive reaction if you go from here to here. Then the reaction is non-spontaneous. Aromatization of alkanes, when we talk of, then aromatization is achieved by catalysts like Cr2O3 or V2O5 or MO2O3 supported over alumina. Alumina is just for support. Basically, the catalysts which are functioning or working are Cr2O3, V2O5 or MO2O3. These are the main catalysts which are functioning. N-alkanes with 6 or more carbons. Okay, 1, 2, 3, 4, 5, 6. 6 or more carbons undergo aromatization. Condition 10 to 20 atmosphere, 773 Kelvin. Now you can remember, see, all of these are OO oxides. OO oxide, and benzene is also OO oxide. So when it is a case of OO oxide, right, then it is aromatization. Is that absolutely clear? Aromatization is when catalyst have oxygen, then it is aromatization. And when the catalyst have all straight sticks, LCl3, HCl, then it is isomerization, linear to branch. Linear, L's are like linear to branch. A very bad method to retain and remember, but it works, then it is fine. If you have more number of carbons here, you will have a corresponding aromatic product. For example, if I have C7N heptane, then toluene will be formed. If I have C8, then ethyl benzene or xylenes. When I draw an arrow from this center, it means that that it is referring to orthoxylene, metaxylene, and paraxylene. All three are considered here. Absolutely okay. Fifth is reaction with steam. When I talk with steam, again, catalyst to be remembered, because what we are producing is important, carbon monoxide plus hydrogen syngas, right? So this is important catalyst to be remembered. Nickel heat 1273 Kelvin. 1273 Kelvin is 1000 degrees centigrade they are talking. Okay, and we are having carbon monoxide and hydrogen. This method is used to prepare hydrogen gas industrially. So with steam at such high temperature, we are producing hydrogen. This is used industrially. Next method is pyrolysis, for which you can directly refer the NCERT portion. I have again used it here. Higher, I'll read it out to you just for revision purpose. Higher alkanes on heating to higher temperature decompose into lower. Such decomposition reaction is into small fragments by the application of heat is called pyrolysis or cracking. Okay, C6H14 is breaking down to C6H12. From alkane to alkene, it can break down to smaller alkenes and a alkane combination. C3H6CnH2 an alkene, C2H4 is ethene, and CH4. Pyrolysis of alkanes is believed to be a free radical reaction preparation. Again, this we should underline, that it is believed to be, not known, but considered to be a free radical reaction. Preparation of oil gas or petrol gas from kerosene oil or petrol involves the principle of pyrolysis. For example, this is a question. For example, dodecane, a constant of kerosene oil, on heating to 973 Kelvin in the presence of platinum, palladium, or nickel over mixture gives a mixture of heptane and pentene. Dodecane is 12 carbon. Okay. This can be asked in question. Dodecane. Platinum, palladium, nickel. Temperature 273 Kelvin. I think this is 700 degrees centigrade. It is forming heptane, pentene, and other products. Okay. So this could be one of your options when PTA3 type something question could be made, or in advance also, because directly from NCERT they are using. Substitution reaction, halogenation of alkanes. This is again important reaction on which so many questions have been asked and will be asked. Substitution reaction when we talk of halogenation of alkanes. So methane plus chlorine, 573 to 773 Kelvin heat. CH3Cl, CH2Cl2, CHCl3 or CCl4. And CH3Cl, 1 chlorine, CH2Cl2, CHCl3, CCl4, all will be formed. Based on the amount of chlorine that you take, or I should say the relative ratio of the two reactants. If I take excess of methane and limited supply of chlorine, I can have mono-halo product as major. And if I take reverse, excess of chlorine, less amount of methane, then I will have CCl4 as major. Okay, but all go to be formed based on the amount of chlorine product is formed. Now, if I talk of mechanism, this is a chain initiation reaction. Chlorine breaking and forming chain initiation reaction. This attack alkane and it abstract at HCl and forms CH3 dot. Now this CH3 dot attack on chlorine and forming CH3Cl and Cl dot. CH4 attacked by Cl dot will again generate CH3. Now see, there is a cycle. This product is reactant of this reaction. And the product of first reaction is reactant of second. So they are in a loop and then they are called chain propagation. That until and unless something is exhausted, like methane is exhausted or chlorine is exhausted, this reaction will keep on going like this. Okay, something has to be exhausted totally in the medium. Then only reaction will come to standstill. And I can't say even the methane to be exhausted. I should better say any H to be replaced should be exhausted. Because if methane is exhausted, I'll be having CH3Cl. So then it will start a reaction to the formation of CH2Cl2. CH2Cl2 if there, then CHCl3. So I will have a reaction to come at stop when all the hydrogens are replaced and CCl4 is formed. Okay, so this is a chain propagation. It is one is happening, is creating a background or a base for a second reaction to happening. Okay, these are initiations. Terminations, when the two radicals just combine, collide, and the reaction comes to stop. For example, chlorine combines with chlorine, Cl2, CH3 dot combining with CH3 dot ethane, CH3 dot combining with Cl dot CH3Cl. These are called chain termination steps. Reaction is coming to stop. From mechanism, it can be interpreted that ease of displacement of hydrogen from alkane is 3 degree greater than 2 degree greater than 1 degree. Why am I saying this? Because the reaction involves radical as a intermediate and the radical stability is 3 degree, 2 degree, 1 degree. Therefore, the ease of displacement is 3 degree, 2 degree, 1 degree. Yes, if I take the same compound and I talk of relative rate of reactivity for different halogens, then it is fluorine fastest, then chlorine, then bromine and iodine. And fluorine is so fast that it is rather explosive, uncontrolled, vague. Okay, it reacts so fast, it is explosive. Chlorine is controlled and useful, irreversible. Bromine is controlled, useful, and very important, it is also slightly reversible. Bromination is slightly reversible. Iodination is highly reversible. Very poor yield of CH3I will be obtained because of reversibility. These two will combine and I'll get I2 and methane. So if I want to make this reaction forward, I need to carry out reaction in a mild oxidizing agent which oxidizes Hi to I2. Hi to I2 is my intention. Why I want only this change? So that by Lee Chatelier, I am removing the product and converting it to reactant. So this whole conversion will make my reaction favorable towards the forward direction. Right? That is why we want a mild oxidizing agent. If I go for a stronger oxidizing agent, only one end I will function. That HI is gone. But if this way, I am attacking the reaction in a double mode. Therefore, I want a mild oxidizing agent like dilute HNO3, which oxidizes HI to I2 and not any further. If halogen is taken in excess, then all possible hydrogens will displace. If hydrocarbon is taken in excess, then monohalogenated products can be formed. Already discussed that part. More reactive radicals are less selective in their choice of attack. This is called reactivity selectivity principle. That such radicals, which are the more reactive, that is like fluorine, then chlorine, then bromine, then iodine is the reactivity. Now, fluorine, if I talk, more reactive. We have already seen the uh, stability factor that F dot will be the most reactive, then is the Cl dot, then is the Br dot, and then is the I dot. Now, F dot is so uncontrolled that it reacts everywhere and causes explosion. So, not to be studied, cannot be studied. I dot is so slow to react that is of no point in studying. This is very fast and explosive. This is very slow. So for us to have any relative study, Cl dot and Br dot are only two available radicals about which we can study what type of radical substitution orders or behaviors are found. Is that okay? So for Cl dot, radical reactivity is of the order 3 degree greater than 2 degree greater than 1 degree. For Cl2, radical reactivity is of the order 3 degree, then 2 degree, then 1 degree. Okay, that is for all basically, but 3 degrees to 2 degrees to 1 degree is found to be 5 is to 3.8 is to 1. So for 3 degree, it has a preference of 5, then 2 degree, it has a preference of 3.8 and 1 degree 1. For bromine radical, the reactivity order is 1600 is to 82 is to 1. 1600 is to 82 is to 1. Clear? To calculate the yield ratio of different products, we have to multiply these reactivity ratio with number of hydrogen. Relative yield will be, ultimately when you are asked the yield, 1 degrees to 2 degrees to 3 degree product yield, then you have to write number of 1 degree H multiplied by reactivity of 1 degree H. Number of 2 degree H multiplied by reactivity of 2 degree H. Number of 3 degree H is multiplied by reactivity of 3 degree H. This ratio is used. For example, first, if I have CH3, CH2, CH3 propane, then 1 degree is to 2 degree because only two type of hydrogens are there. 1 degree hydrogen CH3, CH3, 2 degrees CH2. Right? And all 1 degree are resulting in the same product, 1 halopropane. So I will not treat them as differently. All 2 degree will yield the same product, and that is 2 halopropane. So I will have 1 degree and 2 degree, only two cases. 1 halopropane is produced by 6 hydrogens. So 6. 2 halo is produced by 2 hydrogens. So 2 degree I took 2. And now the relative reactivity. This you need to remember. I understand this is difficult, but Cl dot, it is 5 is to 3.8 is to 1, and for bromine, 1600 is to 82 is to 1. You have to remember that. So 6 into 1, 2 into 3.8 for chlorinated product, and for bromine, it is 6 into 1 and 2 into 82. So 2 degree product is major product in both the cases. In chlorine also, it is formed major. In bromine also, it is formed major. But you can see the percentage dominance of 2 degree in case of bromine versus the percentage dominance of 2 degree in case of chlorine. Is that clear? For 2-methyl propane yield of 1 degree and 3 degree product is 1 degree and 3 degree product is. For chlorination, it is 9 hydrogens for 1 degree. Okay. Yield of 1 degree and 3 degrees. So 1 into 5. For bromination, it is 9 into 1. This is only for 1 degree I have written. Now coming to 3 degree. For chlorination, it is 5 into 1. And for bromination, 3 degree, it is 1600 into 1. So again, you can see the relative dominance of 3 degree. But in chlorination, for this, the major one is 1 degree. Whereas for bromination, the 3 degree dominated, though it had only 1 hydrogen to be displaced. That is the difference. Okay. Coming to 2-methyl butane. Here there are 2 types of 1 degree H. Why I am saying 2 types? Because 2 different product IUPAC names are obtained. When we are asked yield for chlorination, see it is 1 chloro 2-methyl butane, 1 chloro, okay, 3-methyl butane, 2 chloro 2-methyl, 2 chloro 2-methyl butane, 2 chloro 3-methyl and 2 chloro 2-methyl. So if I do what are the products, I am definitely excluding the stereo. Okay, not talking of stereo, just what are the products. So if I talk this, I have 6 hydrogens which will give me this product. So 6 into 1. Is that clear? 6 into 1. Coming to this, if I say this is given by 3 hydrogens. So 3 into 1. Okay. If I talk here, it is 2 degree. So I'll take 3.8 and how many such H? 2. So I'll say 2 into 3.8. Okay. And here similarly 3 degree is only 1 H and 5 is the reactivity. So 5. Is that absolutely clear? So if just structurally which is major is ours, then certainly this is our major because it is having 7.6 as the product yield. Okay, this is 7.6. Here it is 5. And this is 6 and 3. Okay, 2 types of 1 degree H. So we have treated this and this, split it, different. Coming to, if any chiral center is generated as a result of halogenation of alkanes, it will always be obtained as a racemic mixture because the halogenation or the radical involved is always sp2 hybridized. And if something is sp2 hybridized, then it will be attacked from both upside and downside. So for example, if I'm asked chlorine HNU, number of monohalogenated products. So this, there is now scan the entire molecule, nothing chiral. So you'll say 1 product is formed. If I am given this, as I'm saying racemic mixture, so 2 products will be formed, 1R, 1S. So total of this is, answer is 3, 2 this, 1 this, total 3 products are formed for this example. How many products are formed? So you will say answer is 3. Okay, let me say here answer 3. How many structural products are obtained? If just structural, then 2. 2 chloro and 1 chloro. How many chiral products are obtained? Now this was not chirals, only these 2 are chiral. So 2. How many fractions in fractional distillation will be obtained? 2. Because enantiomers will go in the same fraction. They will not go into different fractions. Next question. How many monohalogenated products will be obtained for following compounds? Again, the method is only one. You have to draw each and every structure and then only you will get. Now, isopentane. Monochlorinated, monohalogenated is given. Nothing like that. So, this 2-methyl butane. So one possibility is this. I think I have added one. Say 1, 2, 3, 4. 1, 2, 3, 4. And it was 2-methyl. So second, third, Fourth. So if they would have asked structural isomers, answer is 4. But now you start scanning that when I put Cl here, this is not chiral, but this has become chiral. So you will say 2 products are formed. Here, no chiral, so only one product is formed. Here, this is chiral, correct? So you'll say 2 products are formed. Here, no, nothing chiral, so you'll say 1 product is formed. So answer is 2 and 2, 4 and 5, 6. 6 products are formed. How many monohalogenated products will be formed? So answer is 6. Now similarly, if I go to 3-methyl pentane, 3-methyl pentane answer is 8. Same way you will do the things and you will find wherever there is a possibility of chirality, you have to do that. Okay. And last was methyl cyclopentane. These are the products and answer is 10. Absolutely clear. Be careful while reading the question as monohalogenation is mentioned, dihalogenation, halogenation is mentioned. What is mentioned? Okay. For example, if asked monohalogenated products of ethane, answer is 1. But if asked how many halogenated products are formed, now there is no limit. You have to answer total, whether it is mono, di may be all cases, vicinal, geminal, and then the answer becomes 9. Okay, so what exactly the question is asked? What type? Monohalogenation, dihalogenation, or simply halogenation? That accordingly your answer will keep on changing. So please take care of what exactly is being asked. One very different type of issue is coming for similar question is where you have to be very vigilant. Just check this. If a fixed wedge setting is given, for example, this is given, and now they say that we are introducing chlorine and HNU and how many number of products are formed. Okay, how many number of products. Now, when I do not give formed this wedge dash, like in cyclopentane, it was a different thing. And where here and here you have taken, you can take this is wedge or dash, this is wedge or dash, right? But when this type of wedge is defined, you have to be careful. You cannot change its orientation when you are attacking somewhere else, like CH2Cl. No effect on this. This will be only on wedge. So you'll say only one product is formed. When I attack on here itself, now when it is radical, it could be wedge or dash. 2 products will be formed. Right? But does those 2 products will have any impact on my chirality or GI? No. So I'll take it as 1. Now, if I take here CH3 and I attack here, so I'll say yahan par Cl could be on wedge or dash. 2 cases, correct? But similarly, at the same time, their mirror images at this position, left and right, will also have 2. So 2 for this, 2 for this. Right? But I'm not changing the wedge dash of CH3. That is fixed. Similarly, wedge dash of chlorine, 2 cases, right hand side, then 2 cases on left hand side. These are different. They will be mirror images. Right? They will not be identical. So 2 for this, 2 for this. So if a position is fixed, CH3, if a position is rigidly fixed, you have to keep it fixed in the product. And here again, wavy means you have to take wedge dash. So again, I am allowed to have wedge dash 2 cases for this. You got my point? So let me check the answer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So answer for this is 12. Okay, you got my point. So please be very careful the way question is framed. Coming to one of a past JEE question. I am not having the exact question. Or give me a second, I'll take the exact question, no problem. So that will give you exact idea of what I'm talking of. Give me 1 second. It was a case of halogenation, and they have already fixed the position of one of the bonds. Mhm. You may, yes, here I got this question I'm talking. Okay, this is the one I'm talking, that check the language, check the structure given. Okay, what was the answer given? Let me give you that also. Answer was given 5. Let us see. Are we getting 5? So now, see what is the question. Answer was given 5. Let us see. In the following monobromination reaction, already one bromine is there. This is the fissure. Its configuration is fixed. The number of possible chiral products. You have to be very, very vigilant about the language of the question. So first I have to check how many products will be formed. 1, 2, 3, 4, 5. 5 is the carbon chain. CH2 bromine. Next CH2, no relation to chirality. No relation to chirality. CH3, H and bromine. This configuration remaining fixed. No new chiral center is formed. So I'll say this is my chiral product, right? This is chiral product. Now I take CH3, HBr, CH2, HBr, CH3. This is my new chiral center which is generated. But there are two possibilities. The CH3, bromine H, right? And this middle CH2 has nothing to do with chirality. This remaining like this. So with this chiral center, I got two products. Out of this, one is meso. Okay, that we have to do. CH2. And now similarly here, HBr, HBr, and CH3. CH3, CH2, CH3. This HBr remaining same, and BRH is formed. Okay, moving further, CH3, CH2, CH2, CH3, bromine, bromine, no chirality. And last, CH3, CH2, CH2, H bromine, and CH2Br. It is not chiral. So finally, how many, the number of possible chiral products? This was enantiomerically pure. Chiral. This is chiral. So we'll take this as one. This is meso. So it is a chiral. This cannot be part of answer. See, it is meso. This is chiral. So we'll take this as one. If I check this, there is no plane of symmetry or nothing, and this product is chiral. This is also chiral, right? This is a chiral because there is no chiral center now, right? This is chiral, this configuration remaining same. So 1, 2, 3, 4, 5. Yes, we got the given answer. Answer is 5. So this was the question actually asked in 2016 for chiral products. You may be asked how many products are formed. Then the answer is 7. Okay, how many products are formed? Then answer is 7. So you have to be very careful with the type of language. Or what if in place of bromine, they would have given chlorine? Then even these two, which you are referring as achiral, will become chiral. Because in place of bromine, there will be chlorine, right? So again, you have to reformulate your answer as per the given question. So please be very, very careful with what type of language is asked in the question. Okay, I hope I have cleared the basics required for this particular chapter. Okay, these are the basics which are required for the chapter alkanes. And here hydrocarbon may say first chapter alkanes is over. Tomorrow I'll do alkenes and alkynes. So if any of you have any more doubt, please stay back. Others can leave. Those who have doubt can raise their hands. I'll allow them to unmute and they can ask the doubts. Others, if they have no doubt, they can leave. Okay, so I have two hands. First is Akhila.
Ma'am, can you please repeat the cis-transide point?
Okay, Akhila, I'll try what exactly you're asking. So, cis transide point. See, Akhila, when I talk of dienes, okay, when I talk of dienes, like this. Now, see here, the rotations are allowed. They are not geometrically active, or geometrical isomerism is not present here. Okay, so I cannot call this and this arrangement to be GI, right? This
Yes,
is
ma'am.
like cis. So we are modifying our terminology cisoid. And this arrangement we are calling transoid, like trans. Okay, now rotation is of course allowed. So they can interconnect. But the problem is, what if when that rotation is restricted, as I took this example, see, rotation is restricted, right? They cannot rotate. But if they give you this example, this can rotate. So for example, if they give you on this intentionally 1 mole of hydrogen on ready nickel or whatever catalyst, platinum, hydrogen, whatever, right? One equivalent particularly. So they want to check which to hydrogenate. Now this cannot rotate. You will just go by the simple relative reactivity or relative order of hydrogenation of alkenes. Both are similar. So you hydrogenate one and just close the answer. Okay. Whereas here, see, it can rotate. And if it will rotate, you will have a transoid arrangement like this. Hai. And this transoid arrangement is now suitable for 1,4 addition of hydrogen. I can have hydrogen here, I can have hydrogen here, and it can have pi bond shifted like this. So that is what I said. If it can rotate, you will have 1,4 addition as product. And if it cannot, you will have 1,2 addition. That is wherever the bond is, add the hydrogen and close the answer.
Thank you, ma'am.
Okay, Akila, thank you. Let me check my next candidate. It was Ashish. Ashish, please unmute yourself. I have allowed. Yeah.
Can you say the mechanism of the Woods reaction?
Beta, I could not listen carefully. I could not get the last voice. Mechanism of the reaction.
Woods reaction.
Are you asking Wood's reaction?
Yes.
Just say no. Wood's reaction.
Yes.
You want to know the mechanism of Wood's reaction. Yeah. Okay. So, beta, mechanism of Wood's reaction is.
And another doubt is when we apply the intramolecular and intermolecular Woods reaction.
Well, that is a very, very vast and a vague doubt. Let me first take the first part of your question, okay. That mechanism of Woods. Now, okay. When mechanism of Woods we talk, we have two mechanisms, right? One is radical and other is known to be ionic. And there is no such preference that which to be used or to answer the question. Whichever suits you, you can take. And to explain, I am using ethyl halide, CH3 CH2X for the reaction. Okay, I'm taking this as a substrate. So in case of radical, now how to do the radical? Whenever there is sodium and we take absolutely dry conditions, so dry ether, I am taking solvent. Sodium will release electron, so I will have electrons. Now in CH3, CH2X, carbon halogen bond, this is del positive, this is del minus. If I add electron to positive, I will have CH3, CH2, halide is gone positive, but one electron added, it will form a radical. This part okay? If I take 2 sodium, 2 Na plus, 2 electrons, then 2 every place I do. 2 and 2. Right? Now see when I did this 2 and 2, this 2 NX and 2X, they will combine and twice NX is there in the medium. And these two CH3, CH2 dots, if combined, then I will have ethane, CH2, CH2, CH3, and certainly a byproduct because CH2H, CH2 dot. Last week we did not, radicals can do radical disproportionation like this. So I will have CH3, CH3 plus CH2 double bond CH2 also as a product. Yes. So this is entirely radical mechanism. Now, if I want to go for ionic mechanism, I will have similar observations. Let me go for ionic. Now, in case of ionic, my first reaction is same, that 2 sodium, 2 electron, that part remaining same. So that I'm copy pasting that 2 sodium, okay, they are releasing 2 electrons, dry ether. So 2 Na plus 2 electrons. Now CH3, CH2X, same way, okay, plus 2 electrons. Now here 2 moles were having 2 electrons. Here 1 mole is having 2 electrons. So dot will further accept 1 more electron and I will have anion. CH3, CH2 minus plus X minus. This minus will attack on next alkyl halide. CH3, CH2X like this. CH3, CH2, CH2, CH3, and butane is formed. SN2 we are taking. This is SN2. Okay. And in SN2 also 1 degree is better. If 3 degree alkyl halide, then E2 will dominate. Right? And E2 will dominate. So you will have alkenes as major product. Alkenes as major product. So both explain this observation that if the radical becomes 3 degree, here also if it becomes 3 degree, then radical disproportionation will dominate. Proportionation will dominate. So either of the mechanism justify the entire observation. You can use any. Now, as far as the second part of the question, that when to take inter and intra comparison, when the conditions are similar and both the reactions are possible. In case of intra, it depends whether the orientation of attack is suitable or not. Bond geometries which are involved are suitable or not. So considering all that, if the reaction is feasible, both, then intra always dominates over inter. That is what I can say. Now, when to take is usually reaction to reaction dependent factor. In alkanes, whatever I took now in Wood's reaction, that part is our Wood's and Kolbe's. There you can take the intra reactions for today's content. Okay, Ashish?
Okay, ma'am. You discussed the question in Woods reaction, ma'am.
Okay, so on Wood's reaction, you should take intra when the ring formation from 3 to 6 is taking place,
Yeah.
or when they are vicinal and alkene is formed. So what in a very short way I can say, for Woods we can take when CH2 NX and X NQ value is from 2 to 6. Product ethene, matlab when it is 2 then answer is ethene, then cyclopropane to cyclohexane. Right? Here
Okay.
you can take intra. Okay, so my next candidate is Feisty. Yes, you are allowed to unmute.
Ma'am, for when we use formic acid for Cobley's electrolysis, then H2 is released at anode. But then when we
Yes.
compare the enthalpy values of like H plus and then sodium, then shouldn't it be released at cathode itself?
I could not understand the question. I heard the question, but I could not understand the question. Can you be more explanatory? You are talking of coal-based electrolysis, right?
Yes.
Then in that, what did you ask? That if you take formic acid
Yes,
salt,
ma'am. Then why is it that H2 is released at anode?
okay, then why hydrogen is released at anode in case of
Formic acid.
formic acid? Let me go to the mechanism. Wait, let me go to that particular mechanism. See, in anode, yeah, on anode, whatever is attached at this part, है ना? For
Yes,
example,
ma'am.
if I want to generalize, I'll say RCOO dot is formed. So the final is R dot plus CO2. And there's this R dot combines with one more R dot and you get alkane. But
Yes, ma'am.
it is hydrogen. If this R is H, then here I will have hydrogen. And this is possible only with formic acid. Is that what you are asking, Feisty?
Then, ma'am, when we take like NaOH
Hmm.
and react it with the carboxylic acid, then we have like
RCO.
water releases. And as water releases, the R minus. Okay, yes. Okay, fine. Okay, my mind out is cleared. Okay, thank you.